open for questions. First, to tell you about myself, my name is Jacqueline Silva Martinez. I work for NASA Johnson Space Center. My work is in aerospace systems engineering. And as I was going through different parts of the life cycle of a product, of a mission, I noticed that there is a lot of terms, common terms that we use in systems engineering and space architecture. Looking at the systems requirements first when working with satellites, we do use a lot of the architecture part of it, but it might not be the design itself, but mainly the requirements. Going to assembly and test for Curiosity at JPL, same thing. We were constructing something, but it's the engineering part that took into account the architecture part, and now with mission control similarities. So if you're from one side, from systems engineering or from space architecture, you might have heard these terms of space architecture, systems architecture, or nowadays it's the architecture-based systems engineering. In some countries also might be a different meaning. In South America, for example, when we talk about systems engineering, it's more of the computer engineering that they talk about. And these similar terms of complex design, development and operation, subsystems, or the idea of systems that comes into a holistic view of what the design should be. And the human aspect, and nowadays that we're talking about Mars, we need to include this human systems integration in it. So the idea is that all this mix of disciplines is ill-defined the way it is. So with this workshop or this panel, we wanted to bring this idea and hopefully come up to a certain conclusion of what these two disciplines are. This is not a new idea. There are books and other authors that have been working on it, on trying to figure out what the similarities are. And how is this useful? I think for the Congress team is very appropriate, as it is a collaboration among states and also disciplines. In this case, space architecture and systems engineering, which has a lot to do with the space applications and makes it affordable to a lot of countries. So we need to be working together. The same thing of our space goals. Currently, most space agencies are focusing on going to Mars, and even if we go to the moon or other deep space locations, we need to look at the space architecture and exploration combination. And the knowledge of human systems engineering and integration needs to be more accounted for whenever we do our designs. So in this panel, we'll be asking the questions to these panelists, which is a diverse team. You see women and men here from different places. So we have Russia, Brazil, the United States, the European Union represented here. And they're going to be telling us about one of the other maybe governs the other one, or maybe both disciplines are the same, or maybe they're the same but in a different continuum or same continuum. So we'll be drawing conclusions out of their presentations. So we're going to introduce them first. Olga Banova, she's the director of the Sasakawa International Center for Space Architecture at the University of Houston. She's also part of the Space Architecture Technical Committee, which, by the way, is organizing this panel for you. And she's representing the architecture part, academia, and research. She's also reading a book on space architecture for engineers that hopefully she'll be talking to us about. Dr. Klaus Schilling, he's a professor and chair for the robotics and telematics at the University in Würzburg, yes, and president for Center for Telematics Research Company. He's the chairman for the IEEE Network Robotics Technical Committee. He has a science background in his education and has been doing a lot of engineering getting into academia. Then we have Stefano Ferretti. He's a space policy officer at ESA, project manager for Thales Alenia Space Development in the past, and he has worked with ISS subsystems, and he's going to be sharing his experience on that. And his PhD dissertation is in innovative technologies for space habitat, so he's including both of the sides in it. Background on mechanical engineering and representing industry today. Olga Shatanovich, she is a standardization productions engineer at Agilon for ESA. She is also the co-chair of IAF Global Workforce Development Subcommittee and the vice chair for the Space Education and Outreach Committee. So I'm very representing the education side of it. And she has a background on environmental science and policy, and also representing industry and academia. Dr. Gelson, if I got it right, Ray Gelson Loureiro. He's the head for the Laboratory of Integration and Testing for INPE, the Brazilian Institute for Space Research. He's going to give us the side of the Brazilian aspect of systems engineering, and he represents the ISO and INCOSI, one of the largest systems engineering organizations internationally, and his background is in electronics and quality engineering, representing industry and academia. Victoria is not here with us. She's also a professor, and she's representing IAF, so that's why she couldn't make it. But we have Brent Sherwood, who's the program manager at the Solar System Mission Formulation at NASA Jet Propulsion Laboratory. He's going to be taking the chair for the Space Architecture Technical Committee, and also has a lot of experience with engineering. His background is in both space architecture and aerospace engineering, so representing industry. So we have both sides. It's maybe a fight. In one corner we have systems architecture or space architecture, in the other corner we have systems engineering, but we're going to be hearing from them to understand more what these both disciplines are. And Olga, please, I'm going to ask you to come up.
Hello, everybody. Thank you for coming. And I will start with showing you an animation that a couple of our students worked on. And this is kind of it's representing our approach to space architecture as a discipline, and what we understand under this discipline, this terminology. Space architecture is very inclusive and discipline that has and provides a holistic view on space systems, on human factors, and of course on everything is what is related to architecture when we talk about creating an environment for people, creating a comfortable, safe environment where people can live their close to normal life, but also be productive and creative. So can you please start the movie? For their proposal. project is you cannot design one element like Habitat or Phobos exploration vehicle without understanding how all the systems work, without understanding what people will be doing there. And so you have to design both human activities, understand human activities, what is required for them, and at the same time you design, of course, interior environment and all the elements that are related to, again, providing humans with comfortable and safe and pleasing environment for them, so supporting their physical and psychological health throughout the whole mission. And of course, it's a combination of different systems. It's human systems, it's robotic systems, and then at this point, for example, this automated part, robotic explorers leaving to explore Deimos, unmanned vehicle, and then the whole ship departs back to Earth.
Thank you, Olga. And now we're going to ask Dr. Schilling to also address.
I think the question was raised, what is system engineering? When I left academia and was as a PhD student, when I finished, I was hired in industry by a system engineering department. And I asked my boss what he expects me to do. And his short answer was, at the end of the day, you make sure that everything works. Yeah, so it's like we saw here in this nice movie, you have thousands of components which must cooperate to have a successful mission, to have a successful sample return, and you need all kind of interdisciplinary contributions in order to make a system, a complex system, really working. So that's a big challenge to make things work. And now in academia, we try to educate people to do such jobs. And from this industrial experience, we try to integrate hands-on examples, like CubeSats are now very popular. We work for more than 10 years in integrating CubeSats with our students to have a practical exercise for systems engineering. And this is very well anticipated by industry, not only space industry, but also automotive industry, electrical industry, all look for people who can do systems engineering. Yeah, and space is an excellent example to do such interdisciplinary integration. And yeah, maybe just to point out, such CubeSats are even of interest in industry. Very often they have changes in generations. And young people are very often specialists in one specific area, space dynamics or thermal design. And by experience, you can grow into system engineering, integrating and monitoring the different contributions and disciplines. And so we also run for space industry in the US CubeSat building workshops where the specialists get a view on system integration on a simple small satellite, and they practice this and apply it to more complex missions in future steps. So I think space is a real good background for systems engineering, spreading to a much broader application area.
Thank you, Jackie. So my name is Stefano Ferretti. I am seconded to the European Space Policy Institute as a research fellow by the European Space Agency. And I have a few slides today. Thank you. And I would like to thank Barbara Imhoff from Liquifer System Groups for putting together some of these very nice concepts. So the vision here is that humans have been able to put a man into orbit, then to safely land and return human beings from the moon, and we are permanently living now in space. So we see that there are systems, very complex systems, also robotic systems that are allowing us to embark in very challenging missions. At the same time, we see that we have issues on this planet, and so the Agenda 2030 was put together by the United Nations, particularly with Sustainable Development Goals to be achieved by that time. So you see that there is SDG number 11, which is Sustainable Cities and Communities, and we think that this objective can be achieved both for space, when we think about planetary settlement to be designed and thought for the future, and when we are building cities on this planet, smart cities. So I will take you through a journey which starts from space, from the International Space Station, and you will see where we will end up. So this is Italy taken from space, and in particular you can see the city of Rome, quite a concentration of light at the center of the picture. And this is where initially a certain type of architecture was born. So you see that an arc can be composed as several building blocks and elements into a system that is delivering water. But if you combine this system in a more complex manner, then you may get a building which is fulfilling, let's say, different functions, for example, social functions. So the community element here is there. And here you see a third structure, which was also built in Italy by Thales Alenia Space, which is now in space. This is the cupola. So you see different elements that are composing a window, but this is not only a window. This is actually a system that is allowing for Earth observation, but also for evaluation of cities, densities on the planet. And there is also an inspirational element. We all know the overview effect that the astronauts experienced, and this is thanks to the fact that they could see outside and they could look at Earth from space. This is another concept of a systems of cupolas. This is the auditorium designed by Renzo Piano in Rome, and you see that here again the engineering function, which is to have a sphere in order to optimize the acoustics of the building, is very well composed also with architectural element. So again the function and let's say the inspirational element are combined. And maybe we should also start thinking of these concepts for our future planetary settlement, or for systems where humans are living in space. So music is one of these elements. And here you have a concept of a planetary settlement. So again, you see systems of cupolas put together. And here we have another inspirational element. So this is the Sistine Chapel in Rome. And this is a building which was designed for inspiration. So people should gather there at a certain point in time to be inspired by, let's say, above, in order to elect the new Pope. And so the design and the art which is there is meant for this inspirational purpose. And this is the concept which won the NASA competition for building with 3D printing, additive layer manufacturing on different planets. And the interesting thing is that, again, we see an element which is somehow an uplifting element, and the structure is actually made of water. So what you see there is a nice structure. Here, the journey continue, and so we come here to Mexico. So you see buildings which were designed to observe the universe, so man actually connecting to the universe, looking above and observing the stars and the galaxies and far beyond. So the question is, do we want to have this as well when we think about planetary settlement, and will human beings on other planets also feel the need to somehow connect with the universe? And this is on top of course, the scientific requirements and scientific investigations that will be carried out. I think I finalized my journey in Italy. This is the Pantheon again in Rome, a building designed for ceremonial purposes, also with some health purposes, since some thermae were there. But the interesting element is now space, in particular the sun, is connecting to Earth, and is basically sending a very important message to humanity. So on the 21st of June, a ray of light would hit the opening portal of the building, basically informing the city that summer would start. So again, von Braun space station concept of 1952 is a structure, is a composition of systems actually, where also different functions are conceived, and one is also good health for the people living there. So artificial gravity was conceived, and on the right you have Samantha Cristoforetti on the International Space Station checking out in the US airlock the airway monitoring experiment built by ESA, which is a very complex system designed to monitor the health of the astronaut in space. So the future challenges, both for space travel and for sustainable living on Earth, are composed of several elements that they can be put together with the oikos concept, and at the same time they can link in an interdisciplinary approach with policy, strategy and technology to be put in place. So the idea of a city as a spaceship comes from here. So on the space station there are various elements that are here summarized in the ISS picture, and we can draw a parallel with future cities on Earth, so smart cities. So the energy challenge or the infrastructure challenge can be taken up from future space settlements to Earth settlements, and the same with energy. So we know that in space we mostly rely on renewable sources, so we can also learn lessons, and we can somehow develop new systems that can be used both on Earth and in space for the purpose of sustainable living of the people living there. Technology, automation, and infrastructure, this is a very interesting thing. So the International Space Station was assembled with the robotic arm, so we see that there is a clear interaction between the human element and the robotic element. And without either of the two, this accomplishment would have not been possible. So the ultimate purpose is nevertheless that the inhabitants, the people living into these systems, feel well, that their quality of life is high, and that they can accomplish all the functions and missions that they've been tasked with. So life support systems are now evolving into closed life support systems. And again, this is an element that requires the integration of all the disciplines. So it's not engineering or architecture, but it's also agriculture, health disciplines, but also philosophy, policy, and all the other disciplines. And here we are going towards the end of the journey. So we have a planetary settlement, and we can put together all these elements that we have seen before. So from a space station, from an orbiting station, to a city on Earth, and now back to a city on different planets. So we proved in a way that space is already becoming the link among systems of systems, and its enabling function may therefore represent the new element that will help to bring our societies towards the goal of a sustainable living on this, and I would say other planets for all. Thank you.
Good morning to everyone. So this year, International Space Station marks 18th year in orbit, and already space agencies, international from many countries, are looking for the exploratory space programs outside the orbit of the International Space Station, and they're looking for the Moon and Mars exploratory programs. So Space Agency now at the stage of the formulation of the mission statement and looking into different economic, political objectives and constraints. And here the system engineers are in great need, because system engineers, these are persons or technical experts who put non-technical objectives and constraints of space mission in the technical requirements. So modern and current and new space exploratory programs, they require that the modern aerospace engineers have a system background, a system preparation, and they should have a hands-on experience also from international and interdisciplinary perspective. And that's why the system engineering and space architecture goes together very closely, as all previous speakers shows. I represent here the International Space University, and International Space University we are teaching for already more than 25 years, 3 I's, international, intercultural, interdisciplinary perspectives. And this is what goes with the system engineering. And during the space studies program in summer, we run team project where we have few projects looking on application of space technologies to Earth, but we have also future projects or exploratory project. And I just would like to say a few words about the project that I was chairing in 2008 in Barcelona, when we, with the participants of the Space Studies program, we developed a project called Futurist. We were developing the looking for the space for the infrastructure for the space tourists on ground, because all my colleagues at the panel, they show very interesting perspective of the space habitats in space. But space journey starts on the ground at the spaceport. So what will be the spaceport for the space tourism? And if you are even not really necessary real space engineer, you're architect, you still need to know basics of, say, what is the spaceport and what is the space tourism? Because, for example, and this is what students, they were learning, looking into different perspectives, because to develop a spaceport for space tourism, infrastructure of the future spaceport would develop of the space transportation vehicle. Do you use suborbital flights, or you use orbital flights, or you use point-to-point transportation on Earth? That would define the image infrastructure of the ground infrastructure, where you have a launch pads, where you have special medical facilities, training facilities, where you store propellants. And you need to ask also what are the policies and laws to deal with the local community. Is the propellants and the spaceport activities are threat to the local communities and environment? You also need to look at the policy issue, economic issue, and safety and security. So you see, to my point of view, system engineering and architecture, they goes together very closely.
Thank you, Olga. Dr. Loreiro.
Good morning, everyone. First of all, I'm give you a little bit of background. I come from the Brazilian Institute for Space Research, and there, in Brazil, this institute is responsible for space missions definitions. And once we have the space mission definition, and we get to an architecture, mission architecture first, and then product architecture, satellite architecture, then we subcontract the subsystems from industry. Once industry develops their design, the laboratory of integration testing, we buy the components for them, and we buy the components, specify the components with space qualification requirements, and then these components are then delivered to industry. They build their equipment. The equipment come to the laboratory of integration testing. They are then tested there, environmental testing. When they are ready, they are integrated in a full satellite that is also undergoing tests, environmental tests and functional tests. So this is how it is in Brazil. In Argentina, for example, they have CONAI, which is the agency, sort of agency, Argentinian agency, and they are the ones related to missions. And they have also an integrator company called INVAP, and that company is responsible for example, delivering satellites. Completely different approach, those two countries. What we see is that the confusion comes from the fact that we develop a space architecture, and then for using systems engineering, and then for each of the systems in there, we will also have to do systems engineering and then develop the architecture for that system, and so on. So there is no such a thing that one thing is inside the other. We do it in layers, and we do systems engineering to get to a system architecture, and for each part of the system architecture, we do systems engineering again to get to the architecture of that part, and so on. What I'm going to present to you here are some slides related to the view that we want to develop in Brazil. So these are the questions that we are supposed to answer here, but this is the concept that we use for systems engineering as a collaborative, multidisciplinary engineering approach. Systems engineering is a way of doing engineering, is not the way of doing engineering. To derive, develop, and verify a system solution. The solution is not only product. That's why we write solution there, because we need to have product and organizational elements in that solution. That is balanced along the life cycle, not only for operations, but for the whole life cycle of the system, and that meets stakeholder expectations. That's adapted from IEEE because they didn't include the stakeholders in their definition. They only used to say public acceptability, but we understand public as only one type of stakeholders. So the way we see it, we see systems engineering as a discipline as well, and as part of the systems engineering discipline, we have systems analysis, systems architecting, and systems management. So there is a difference between systems architecting, the process, and systems architecture, the result. So here's the systems engineering process, and you see the system architecting as part of the whole systems engineering whole. This is what we call systems architecture. Systems architecture is a composition of context, structure, behavior, and a stepwise decomposition. What I've just told you, we do systems engineering at a space architecture level, and then at a segment level, and then at a system level, and all of them will result in an architecture. So here's a proposed approach. We need to do systems engineering, systems architecting, considering that we must do that for product and for organization at the same time. For example, if your development organization is also responsible for disposal, for example, or decommissioning, you must think of the decommissioning organization at that time, during the development, during the beginning. So the traditional systems engineering is product-focused, and concurrent engineering can add to that effort, considering also organization, but not only organization at the very low level of abstraction, but also at the top level of abstraction. This is a traditional mission architecture, from launch up to the suborbital vehicle that we are developing in Brazil. This is a traditional mission architecture, but the actual mission should be described as this one here. It should include all life cycle processes along the way, because there will be no success if we forget to plan the transportation, for example, of that vehicle to the base, for example, or it won't be any success if you don't think of the data acquisition effort at the end of the mission. So we propose then, we understand that it is possible to develop product and organization at the same time. At your right-hand side, you have product effort. At your left-hand side, you have organization effort. And if we do that, if we do those both efforts at the same time, we can gain along the way. So, in conclusion, systems engineering is an approach and a discipline. The systems engineering encompasses systems architecture. The systems architecture is the result of systems architecting, and the systems architecture must encompass product and organization elements of the system solution. Thank you.
Thank you.
So you've heard some very insightful comments from the other panelists, and it's great because I don't have to repeat a lot of these important points. I'm going to just say a few remarks that get right to the question in the title of the session. And my position, as Jackie and Olga know, is that architecture and systems engineering are two different things, very different things. But as you've heard earlier in the panel, you must have both for success. So I've had a foot in both worlds. I have master's degrees in both fields, and there's a reason for that. It's because they are different. They teach different things, they seek different skills, they exercise different ways of thinking. And I just want to say a few things about why both are necessary. So some of the most brilliant systems engineers that I have worked with are superb architects. They don't have a degree in architecture, but that's irrelevant. What matters is how they think. And so Gelson just explained why in this classic V formation of systems engineering, the way we teach and execute systems engineering, systems architecting is critical. That's the first half. That's the derivation of all the sub-tier requirements that define a system and what it's supposed to do. And as Klaus said at the beginning, the systems engineer is the one who at the end of the day has to make sure the thing works. And that's done through verification and validation. Verifying means that you built the thing right. Validation means you built the right thing. That the thing you built will, in fact, implement the purpose for which it was intended, even if it encounters conditions that weren't thought about explicitly in the design process. And successful architecting accommodates that operational flexibility. That's what architecting is. So why are they two different fields? The way I describe it is that systems engineering is analysis responsive. Okay, all of engineering is analysis responsive. You ask a question, you confront a requirement, you perform an analysis, you see the results of the analysis, and then you determine what to do next. Architecting is design directive. That means it establishes a vision and then works toward that vision. In the extreme, in the world of terrestrial architecture, you may have an architect who uses only a pencil on a piece of paper and only cares about the vision. Philip Johnson was an example of that. Brilliant architect, creative, innovative, extremely long career, made many breakthroughs, had no idea how to build a building. By the same token, you can have a system which is successfully engineered, but which is not a pleasant place to be. Now, when you're doing robotic space missions, the architecting is this structure of requirements that you develop. And that's all you need. It doesn't have to be pretty. It doesn't have to be happy. It just has to work. When you start putting people in space, then you start to need real, traditional architecture. Because human habitation, human environments are not just functional. They cannot be only functional. By the way, if they're designed by engineers who work in government buildings that are not typically very inspirational, it would be no surprise if you ended up with a facility which is perhaps not the most conducive for a healthy, happy crew on a 600-day mission to Mars. So the way I would encourage you to think about the contrast between the two is this skill-based difference, analysis responsive versus design directive, and you can see why you need both together. But also to go back to one of the earliest definitions of architecture by one of the earliest documented architects, and that's Vitruvius, who said that architecture is three things: firmness, commodity, and delight. Firmness means, does it stand up, right? Can it be built? In space system terms, it means, does the structure work? Does the thermal system work? Does the power system work? Commodity means, is it usable? Can it be used for the function for which it was intended? Okay, and in space systems, that means human factors engineering and functional analysis. Delight is the third piece. If you're on a 2-day mission and you're a highly trained mission crew member, an astronaut, the delight part doesn't really matter. But if you're a crew of 4 or a million, as we heard the other day, and you're going to a very far away place, extremely hostile environment, with significant risks you may not make it back, you probably need some delight. It's a long journey. Space is extremely boring and hostile, and it takes more for human habitation than simply firmness and commodity. So our argument as space architects is that as we begin to solve the problems of survival and utility in space with humans, which we're just at the beginning of, But in this century, as we solve those problems, then the old traditional problems of human habitation will start to arise. The issues that have to do with psychology and sociology and whether human communities are thriving, creative, inspired, and that's where space architecture will begin to come to the fore. Thanks.
Thanks, Brian. Thank you to all the panelists for giving us their approach for what the systems engineering is and what the space architecture is, and maybe the mixing part that we have there, or maybe separation. I wanna ask you, all the audience, to think about the questions that you wanna have for the audience, and maybe they can help us with the mics. But first of all, start with those that are representing academia. Are we preparing our systems engineering well enough to go into space architecture jobs? And similarly, for space architects, are they getting involved with systems engineering? How are you infusing that in your curriculum? Maybe Olga, you want to start?
I can start on that. Well, a few of our graduates do work at NASA, and they work for Boeing, and worked for Bigelow for a while. First, I think they were seen as system engineers, so those who understand the systems. But then more of their architectural background was appreciated more and more as they continue working. And now they do work, I would say, more as a space architects, but with necessary background and understanding of systems, understanding what is involved, understanding of the requirements and constraints, but looking beyond those constraints from architectural perspectives. And that is what I think the most valuable, because you can look and see problems from different sides, from different perspectives, and come up with a unique and more connected to other elements of the mission solution that will also guarantee the mission success at the end.
Yeah, I think we have a lot of tools we can rely upon, and many management procedures, many processes have been developed in space, because we encountered here very complex systems we must handle somehow. Like sometimes Apollo period, process management was quite advanced those days. And so we learn tools, but I think it's very essential that we also learn to apply, that we really try to have hands-on specific problems, that in education we solve real-world problems and practice applying these engineering tools, these architectural tools, that we really suffer from the deficits when we make failures. And I think in education we must train our people to learn from failures. Yeah, lessons learned, that's experience. And experience is a key to do meaningful architectures, to do meaningful systems engineering.
At the International Space University, I witness a bit reverse effect when few architects, they come to the Space Studies program, Master of Space Studies program and summer program, and they were studying interdisciplinary aspect and system engineering of building space missions. And then we have even one successful graduate, Andrei Dole, who was even trying to build a space architecture program, master program, between his university in Prague and International Space University. I would say, and then reverse, the participants, the space engineers, of course, when they build work in a team project for the exploratory project like Moon Base or mission to Venus, of course, and Mars habitats, of course, they look into different aspects of the building Mars habitat, from the shape to the psychological aspects and life support system. But of course, from the practical point of view, we are now, it's very difficult to build such exciting space program as space architecture. It's Olga maybe know, because maybe in the world until now there is only one university in USA who are giving courses in space architecture. So it's very novel field, but very exciting, and maybe it needs support of space agencies for this. That we have more courses of space architects.
If we started 10 minutes later, so I think we can gain those 10 minutes back for questions. If there's any questions on the floor, please, here in the front.
Hello. Thank you for your presentations, for your talks. My question is regarding the industry, so perhaps it's to the members of the industry. As far as I know, there is no such position as space architect. You were talking a lot about how they're different. Is there a trend to separate those two, to employ space architects and space system engineers, but not like differentiating them somewhere in the future? Is there any trend for there to be such a position as a space architect? Thank you.
I can start. That's a great question. Let me just say three brief things. One is there have been roles, particularly at the Johnson Space Center, for space architects on teams working on habitation systems. Chris Kennedy and Larry Toops are the primary examples of that. At Boeing, when I first started my career in 1988, our organization manager, we were responsible for concept engineering of human missions to the moon and Mars. He had a habit, it turns out, of hiring architects. There's a role in engineering called a systems configuration designer that overlaps with a lot of the same skills that architects develop. And Gordy used to hire architects into that role. I was one of those in '88. And I asked him, why do you do that? And he said, because architects think differently. Some engineers are very good at learning how to architect, but architects are trained that way from the start. And the third thing I'll just observe is, perhaps coincidentally, there are 3 space architects at the Jet Propulsion Lab, even though we don't do human spaceflight there. That's because the integrative way and design directive way that architects think is extremely useful in an organization, and you've heard that from some of the other panelists. It's this uniquely human ability to have a lot of information and integrate it together into some solution to a very complex problem, something no machine on the horizon can do. So I do not know of many, really, if any, named role programs for hiring architects, but you will find architects scattered throughout the industry because of the way they operate.
Thanks, Scott. And Dr. Lorero, can you share with us what is done at INPE, maybe? Yeah, Lorero.
The way I see, if you think that systems engineering can be split in systems analysis, systems architecting, and systems management, you see clearly three different profiles for those jobs, I would say. So the systems architect is the one that will come from the need up to a proposed solution. So he has to have those abilities in terms of be open for understanding the need and for providing solutions that are maybe no one never thought of. The analysis, you must have a more mathematical background, maybe knowing more analytical background. And for the management, you have to have managerial abilities, managerial skills. So it's very hard to find these three profiles in one person. So if you split the systems engineering discipline into those three ones, I think it's easier to find the appropriate people for those.
Thank you. And one last question here. We're running out of time. Thank you.
Okay, I would like to give one comments. I am from Russia, from Kazan Chitaev School of Stability and Mechanics. So my comments, such statement is not correct because any object, any system in engineering application, also theory, it is multidisciplinary object. This statement was like in Soviet Union time, also in Russia, from 1920 years. Maybe you know name Vernadsky. Vladimir Ivanovich Vernadsky. He is academician of Russian Academy of Science, and he told in 1926, he is founder of very, very interesting theory about noosphere. What is this noosphere? It is we, mankind, and space. So it is one system. And he told, we specialize not in sciences, but in problems, because any problems don't pack in one single science. Do you understand? Mm-hmm.
Thank you for the comment.
So from my position, it is necessary correct this statement.
Mm-hmm. Thanks. Just for final remarks, thanking again. No, they told us that we ran out of time, but thank you. So while the architects and engineers' education might be different, the complex systems or systems of systems that we discuss about, particularly in human spaceflight, demand that we learn many different disciplines, and we learn about them today as well. We need to become comfortable with the fact that systems have cross-cutting implications and complex system performance, and it's affected by how smooth and well-matched subsystems are at their interfaces. Hence, now that our vision is on missions to deep space, we need a combination of both disciplines, space architecture and systems engineering. So thanks again, the panelists, and thank you for being here.